Have you ever wondered about the invisible world beneath the atomic level? What if we told you there's an equation that holds the key to this microcosm? Enter the Schrödinger equation, a wave equation that has been a cornerstone in our understanding of quantum mechanics since its inception in the early 20th century. Crafted by physicist Erwin Schrödinger in 1925, this equation was born out of a quest to comprehend the behavior of electrons within atoms. At the heart of this equation lies the wave function, a mathematical expression that describes the probability of finding a particle in a certain state. It was Max Born who, in 1926, shed light on the true physical interpretation of Schrödinger's wave function, thereby introducing probability into the realm of quantum mechanics. From the theory of ultra-cold atoms to the workings of lasers, the Schrödinger equation has found myriad applications and sparked countless philosophical debates. So, what makes the Schrödinger equation so critical? Let's delve deeper. At first glance, the Schrödinger equation might seem intimidating, but worry not, we're going to simplify it. Let's start by breaking down the equation into its various components. The equation is typically written as HPs equals sign EPs. Here, psi represents the wave function, which essentially describes the state of a particle. It's a mathematical representation that tells us the probability of finding a particle in a certain state. Think of it as a roadmap of all the possible locations a particle could be at any given time. Next, we have the H, which represents the Hamiltonian operator. This is where things get a bit tricky, but bear with me. The Hamiltonian operator is a function that represents the total energy of the system, and it's split into two parts: kinetic energy and potential energy. Kinetic energy, as you might already know, is the energy of motion. In the Schrödinger equation, it's represented by the term involving the second derivative of the wave function. On the other hand, potential energy is the energy that a particle possesses due to its position in a field of force. For example, if a particle is in a gravitational field, it will possess potential energy relative to its height above the ground. In the Schrödinger equation, it's represented by a term involving the potential function Vx, which depends on the position of the particle. The last component, E, represents the total energy of the particle. It's the sum of the kinetic and potential energy. When we solve the Schrödinger equation, we aim to find the wave function that makes the equation hold true for a given total energy, E. So that's the Schrödinger equation demystified, but what does all this mean in the grand scheme of things? The Schrödinger equation is more than just an equation. It's a key to understanding the mysteries of the quantum world. In its essence, the Schrödinger equation has helped us unlock the universe's quantum realm. This is a world where particles can exist in multiple places at once and where the act of observing can change the observed. It's a world that defies our everyday intuition, and it's the world that the Schrödinger equation describes. One of the most significant implications of this equation is its application in the study of ultra-cold atoms, plasmas, and lasers. In the case of ultra-cold atoms, the Schrödinger equation guides us in understanding their behavior at near absolute zero temperatures. This understanding has led to breakthroughs in the development of ultra-precise atomic clocks, quantum computers, and even new states of matter. When it comes to plasmas and lasers, the Schrödinger equation helps us model and predict their behavior. This has opened up a vast array of applications, from plasma TVs and neon signs to laser eye surgery and fiber optic communications. But the implications of the Schrödinger equation go beyond the practical. They delve into the philosophical. The probabilistic nature of quantum mechanics, as revealed by this equation, was a point of contention for Albert Einstein. He famously said, "God does not play dice with the universe." Einstein was uncomfortable with the idea that the universe at its most fundamental level is governed by chance. But the Schrödinger equation disagrees. It says that at the quantum level, uncertainty is not just possible, it's inevitable. This equation has irrevocably changed our understanding of the universe. It's shown us that the world is far stranger and more mysterious than we ever could have imagined. It's challenged our perceptions, our philosophies, and our comforts. The Schrödinger equation, thus, remains one of the most important and mysterious equations in physics, and its exploration continues to unravel the secrets of the universe.